Okay. I suppose this is where we stopped yesterday, and so we can continue from here. Um, this is a solution when we have two beams on the two sides. So it is not half width microstrip as you can see, and it is a different order. The previous order, first order one has a null in the middle. This is the second order, so it's not the fundamental, it's not the first order, it is the second higher order, EH2 mode, that has more variation along the width, more field variation in the middle is going down, in the sides going up. So these two edges are like radiating edges, radiate. So it can be implemented in a full width microstrip line, a little bit wider than normal. But excite in this mode is little tricky because when you try to excite a higher order mode, you may excite the other modes also. So we want to suppress some of the other modes, the fundamental and the first order mode. So for that, we add a septum or short in the nulls of this mode. So here you can see there's a null, here there's a null in this mode, but they are not nulls in the other modes. So if we put a short here and short here, then the other modes cannot be excited, and it becomes easier to excite this mode. So it could be a septum continuous, but in practice, as I said last time, difficult to implement a vertical conducting wall, but instead you can have a series of vias. So that's the purpose of these vias, two vias arrays and the two sides in this location. The rest is very much similar to what we discussed last time. Transition section and so on. So you can find the details in this paper in transactions. And the results. Frequency versus beta diagram, omega beta diagram. That's a light line. So this is the band in which it radiates, right? Frequency band. And we change the frequency, it changes the beam direction. So using the same formula that you saw yesterday, the beam direction theta can be plotted versus frequency. And these are the dispersion curve is by dispersion analysis, full wave simulation, and by full wave simulation of several antennas with different lengths, 8 lambda naught, 12 lambda naught, etc. So it's not a massive change in the theta. And this is the simulated field distribution. You can see the vias and the null here, the edges that are radiating, and the nature of the field. This is at 7 gigahertz. So these are the predicted and measured S11 input reflection coefficient of this dual beam leaky wave antenna. From the prototype is measured S11. Actually, it has S11 and S21 both. So this is S11 input matching. It's reasonably good, less than minus 10 from here. Some mismatch at the lower frequencies. The S21, remember from yesterday, this is the loss. This is the power. This represents power that's going to the load, match load. And we don't want to have, we don't like that, right? It's all total loss. But that is very, very small, it's minus 40 dB. Only at very high frequencies you get, still it's quite small amount of transmission or loss at the match load. So 10 dB return loss bandwidth is 23% here. It's very large for a dual beam microwave wave antenna. At that time, I don't know now. There may be better ones now. With the wide impedance band, this is essential to achieve beam scanning over wide angular range by sweeping frequency. So at that time, the previous best was 7.7%. So 23% was a very large improvement over the best at that time. The leakage constant alpha versus frequency, it's difficult to measure this. You need to probe and work out various ways. It's easy to predict from the simulations, but the measurements are fairly fine at higher frequencies. Not here. In general, alpha decreases with frequency. So higher frequencies decay slower, right? Less alpha means slower decay. They decay slower, and that's why at higher frequencies you have S21 here, increase in S21. So there's some power that was not radiated due to low alpha, and some power left over at the far end, and that goes to the matched load and giving this S21. At low frequencies, alpha is large, so it attenuates very well and radiates, and nothing left at the when it reaches the match load. The beams and the beams and how they change with frequency. So first one is for 7 gigahertz with increase in frequency. The last one D is 8.75 gigahertz. Now these are somewhat strange radiation pattern cuts. These are on constant theta cones, because you know the theta is the beam direction, beam peak direction. The beam peak, theta value of the beam peak changes with frequency. At low frequency, the theta of the main beam is 73 degrees. So to plot that, we made a pattern cut on a constant theta cone. Theta equals 73 cone versus phi. To understand how the beam changes with phi when theta is fixed. So you can see the peak here. These are normalized, but you can see the peak. These are the two beams. And the main beam is theta. And main beam phi value you can find from this graph. At the other end, high frequency end, main beam theta is 38 degrees. So we make a constant theta cut cone on a cone. And then from that you can find the phi value of the main beam. And then same thing you can do on the constant phi planes at each frequency. So for example, at 7 gigahertz, this is the cut on phi equals 48 degree plane, which is the phi value of the peak, beam peak at that frequency. So by looking at these two diagrams, you can work out the phi value, theta value and phi value at each frequency. At 7 gigahertz, beam peak is at theta equals 73, phi equals 48. At the highest frequency, beam peak is at this one. Beam peak is at theta equals 38, which is also shown here, and phi equals 60 degrees. That is this cut, and this peak is at 60 degrees. So it's a little bit unusual to standard constant standard like theta cuts, constant 2D pattern cuts. But that is necessary to understand this strange, unusual nature of these beams. Another way to put it, put the beam contours versus elevation and azimuth angles, phi and theta. So this is at 6.92 gigahertz. You can see the beam peak, theta, and phi values here. That's one beam, and this other beam, theta and phi values. Measured gain and directivity. The dark, so black curve is directivity. Blue curve is gain, both measured. Gain and directivity are very close to each other at lower frequencies. At higher frequencies, there is a difference, less than a dB, but there's a difference. I think you can guess the reason for this, right? That is the S21. That is the loss. Go to the match load. So at higher frequencies, we have some power terminated, going to the match termination, and as a result, radiation efficiency decreases. So a gap emerges between directivity and gain. The measured peak gain of the antenna is 12.7 dBi. I believe that is, I forget which frequency actually. Oh, it's at the highest frequency. That's the peak value. And the variation of gain is 6.92 to 8.75. In this frequency band is 3 dB, 3.1 dB. So this is a summary of the performance of that frequency, beam direction measured and predicted. This is theta value of the beam direction measured and predicted. And this is the phi value of the beam peak. Because we have two beams. One is at plus 48, other one is minus 48. That's a plus or minus. So when you change the frequency, you can see the theta decreases and phi increases gradually in this type of antennas. So this is about a different class of leaky wave antennas. I said yesterday, okay, sometimes you can't change the frequency, but you still want to steer the beam, right? You're not allowed to change the frequency. Frequency is set by the regulations. So how do you change the frequency, change the beam direction to steer the beam of a leaky wave antenna without changing the frequency? So for that, you have to change something else. So you have to make the antenna reconfigurable. These are some of the antennas designed that way, reconfigurable left and right hand leaky wave antenna, composite right left leaky wave antenna. That means this transmission line behaves like a right hand transmission line at some frequencies, left hand transmission line has other frequencies. And this is one of the original ones. published by Christoph Carlos and Tatsuo Ito. That's the professor in University of California, Los Angeles, UCLA. I could not remember his name yesterday. A good friend of mine, Tatsuo Ito. He was the one who published the uniplanar compact artificial magnetic conductor with one of his, I can't remember, one of his students or postdocs. Okay, going back to this topic. So you got varactor diodes. They are inconfigurable. You can change the bias of the varactor diodes. By changing the varactor bias, you can steer the beam of this antenna. Not a lot, but a little bit, without changing the frequency. Frequency is always 3.23 gigahertz. So scanning from minus 10 degrees to plus 7.5 degrees, measured gain, all negative because this is very, very lossy antenna. Directivity is positive, but when you add the losses of the varactors, etc., the gain became negative due to the poor efficiency. And also you have to apply various bias voltages, 0 volt, 9 volt, 35 volts to get these three beams. 0 volts, 9 volts, 35 volts are the bias voltages. So it basically has three beams, switch between these three beams. It's not complete beam scanning, it's just switching between three beams. But if you apply other bias values, you can, I believe you can continuously steer the beam between these limits, minus 10 degree and plus 7.5 degree. This is another one with another group in UTS with some Spanish collaborators. That's quite complicated system. This is based on the 1D Fabry-Perot leaky wave antenna, which we published, my group published earlier. Andrew Wiley was my postdoc before. So he published, I will describe that in my other lecture on resonant cavity antennas. And then he moved to CSIRO and worked with this group with the collaborators, and he extended it to a reconfigurable antenna. Now this is the one we designed to do more substantial beam steering without changing frequency. So fixed frequency beam scanning using binary switches. Okay. So again, we have to change something. What we are changing are the status of binary switches. Otherwise, this is a standard leaky wave antenna. The difference is you have lots of switches along one side. So it has a VR array for, it's not here actually, it's here. Transition, feed line, match load, all pretty standard substrate, microstrip transmission line. What is uncommon are these patches. Each patch is connected to a switch with a VR. I will show you all the details. So length of the antenna is 4.5 lambda naught. Lambda naught is free space wavelength, and you can find more details in this paper in IEEE transactions on antennas and propagation. So there's a patch here. This is not a microstrip patch, radiating patch. It is just another smaller conducting patch. This is the microstrip line, and you can see there's a tiny gap between these two. that provides DC isolation between the patch and the line. So that way we can bias these switches individually. The other end of the patch has a via. So now got another figure showing the same thing, the microstrip line, this patch, the gap, and the via, right? This is just one element of this periodic structure, or could be periodic, could be aperiodic. Some more details here, the patch, and now you can see a via going from the patch down to the ground plane level, and this is the ground plane. Lost my mouse. Okay, this is the ground plane. So when we bias, we apply 1 voltage to the ground plane. Then to accommodate the switches, there is a slot here. We remove the ground plane, and inside the slot there is another patch. We call it bias pad. So the VI is from the top patch to the bottom bias pad. So the switch is between this bias pad and the ground plane. So each bias pad and the ground plane has a switch. And you can turn the switch on and off by applying a bias voltage to this patch. That is not shown the bias line, so each patch has a bias line, very narrow line. It's electromagnetically insignificant, but because of this gap, we don't, the DC value, there's a DC isolation between the voltage we apply here and the voltage we apply here. So we can turn on this switch by applying the right voltage to this bias pad, and we can turn off this switch by applying the correct voltage to this patch, and so on. So every patch gets its own bias voltage, but this is binary. This is not varactors. These are not varactors. These are on and off switches like pin diodes. Okay, so we don't need the whole range of bias voltage values. We need only 2 values. One voltage to turn off. 1 voltage is applied to all the switches that are turned off. 1 voltage is applied to all the switches, not to the switch directly, but to these patches to turn on the switches. Okay, so it's a bit complicated, but the configuration, but you can find, you can look at these figures carefully in the paper. So now the analysis is sometimes can get complicated. So this is binary unit cell. Each piece in the antenna is a binary unit cell, right? So we represent each unit cell by this block. And depending on the state of the switch, it could be in state 1 or state 0. So the whole antenna is series of binary unit cells. Several number of binary unit cells. Pretty much you can apply any binary combination you want. For example, if you have 24 switches in this antenna along the length, 24 unit cells, then how many binary combinations you can have? 2 to the power 24, right? 2 to the power 24 different states this antenna has. And that is massive, and analyzing all of them is ridiculously complicated. but also not necessary because some of these have very similar performance as an antenna. So what we did, in order to systematically analyze in a simpler way, we combined several binary unit cells to make a one macro cell. So this is, suppose you can combine 4 binary unit cells to make one macro cell, and this becomes your macro cell. And it's represented by this red box. That's a combination of 4 binary cells. So if the 4 binary unit cells have binary combination 1, 0, 0, 0, the macro cell has a state of 1, 0, 0, 0. And we assume that this is periodic. So the next one is also 1, 0, 0, 1, 0, 0, 1, 0, 0. Now it becomes a periodic structure. So we can analyze it as a periodic structure. Binary patterns of macro cells correspond to complete binary patterns of a 1D periodic reconfigurable structure. M equals 4 means there are 4 binary unit cells in one macro cell. So we denote it by M4. And each macro cell has 4 bits. So each macro cell could have 2 to the power 4 different states, right? 2 to the power 4 different states, and these are listed here. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, so on. Those are the 24. And then, so here it's shown one state, 1, 0, 0, 0, and then we gave names to those. This is basically converting binary to hexadecimal or decimal. So 0, 0, 0, 0 is M40, 1, 1, 1, 1 is M415. That is the state of the macro cell. Those are the 16 possible macro cell states, 0, 0, 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, that is 1, 1, 1, 1, 1, 1, 1, and all of them are ones. From all of them to zeros, from all of them to ones. So we call this a complete binary pattern. The complete binary pattern starts from 0, 0, 0, all zeros to all ones, and all these combinations in between. But that is combine 4 binary cells into one macro. If you want, you can combine only 3 binary cells to one macro. Then M equals 3. Then there are only 8 independent states of the macro, 2 to the power 8. If M equals 2, that is only 4. Okay, so we applied these complete binary patterns to this antenna and simulated this. So these are the radiation patterns for 6 macro states. 6 macro states. Starting from M40, okay, which is this M40. That means 0, 0, 0, 0 repeats. So that means all the switches are off. If that is the case, radiation pattern is this. Okay, the pink one, that has maximum theta, maximum steering. And then the other end, M415. M415 is the one here. M4 state 15 means 1, 1, 1, 1, that repeats. So all the switches are ones. That is the other extreme, and this is the radiation pattern. This is the gain pattern, and this is the beam direction. That's around 30 degrees theta. So by applying other patterns, by applying other binary patterns, you can steer the beam between these two extremes pretty much to any direction you want, almost any direction you want. For example, M45 pattern gives this beam. So you can check what M45 is. M45 is this. That is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. That's it. Okay. And if you want, you can combine 8 of them into one macro cell M8. I will not go into those special cases, but you can see that we only need few binary patterns to steer the beam across from minimum theta to maximum theta, the whole steering range. You need only for 5 binary states. The others are irrelevant unless you want to steer the beam with very small steps. Some binary patterns are the same, gives almost the same radiation pattern. So this is M41, M42, and M48. They give the radiation pattern and so on. So because it spent quite a bit of time now, I think we will move on. Now what about this gap? This tiny gap G? What is its role? By changing G, you can change the beam scanning range. When G is 0.5 millimeters, beam scanning range is from 35 degrees to 49 degrees. It's only 14 degrees. When G is 0.1 millimeter, you get very good beam scanning range from theta equals 32 to 63 degrees, that's 31 degree beam scanning range. So these are some of the plots with different G values. With G equals 0.1, you get good beam steering. With bigger G values, you end up with a narrow beam steering range. Okay, now this is something we haven't looked at so far about the current distribution, surface current distribution along the length of leaky wave antennas. Remember my cartoon type figure in the beginning had an exponential decay, right, of the electric field and current, etc., the power in the leaky wave antenna. And as I said, it decays with length, and in some of them it becomes almost zero here. So this is a good example for that. So this is the current distribution of only 2 antennas. These both of them are for one antenna, which is a standard leaky wave antenna, no switches. So we change the beam direction by changing frequency. The other 3 are again for one antenna with switches. We apply different binary combinations to get different beams. So starting from this one, first one, it's a uniform half-width leaky wave antenna at 5.66 gigahertz at a lower frequency. The current decays very rapidly. It's almost zero here. So when that happens, the effective aperture of the antenna is short. That means directivity is less, and aperture efficiency is radiation efficiency is very high. So the gain is almost equal to directivity. And this is what we saw in the beginning, right, for this kind of antennas. Now this is the same antenna at a higher frequency, 7 gigahertz. Now alpha is smaller and it does not decay very well. and there is some energy left over, and that is absorbed by this load. I think this related to the question yesterday, right? This whether this is a two-port device. We've got two ports, and yes, now it behaves like a standard two-port device with some energy. If you look at S21 from port 1 to port 2 is not insignificant in this case. Here it's negligible, here it is not negligible. Good thing about these antennas is effective aperture is almost full length, so they have very high directivity at higher frequencies. But because of the loss, the power going to the match load is a loss. Radiation efficiency is less, so gain is not equal to directivity. Gain is a little bit less than directivity. When you look at any leak wave antenna, you can work out these properties. The kind of universal. Now, what about the leak wave antennas with switches? So configuration C, it is our leak wave antenna with complete binary pattern 1, CBP1 at 6 gigahertz. And you can see that it has a stronger alpha. It decays very well and very little power left here. And also effective length is smaller than the length. So its directivity, we expect less directivity from this, but high aperture efficiency. Now we change to other patterns. This is complete binary pattern 3, and this is complete binary pattern 5. At the same frequency, you don't change the frequency now. The same antenna, same frequency, only thing we change are the binary pattern, complete binary pattern between 1, 5, and 1, 3, and 5. I did not define this, did I? So where is it? I had, here they are. These are the complete binary patterns. This is CBP1. That means all of them are 1. 5 is all of them are 0. And 3 is 1, 0, 1, 0, 1, 0, 1, 0. So these are the distributions for those 3 patterns at the same frequency. And they have different beam directions, they have different characteristics, different directivity, and so on, but they behave just like the ordinary leaky wave antennas where you change the frequency. Here we don't change the frequency, we have fixed frequency, but we change the binary sequence, but you get the same effect. Change the beam direction, change alpha, change beta, change beam direction. So these are more binary radiation patterns of this antenna. And these are actually for ideal switches and actual pin diode switches. We put in the model of a pin diode into CST. So you can see the difference between the ideal switch case and the actual pin diode case. Due to the loss of the pin diode, there's in some cases, there's the drop in gain by a dB or so, and that is due to the loss of pin diode when the diode is on. Summary of these results. For different macro cell states or complete binary patterns, I have shown you before the measured return loss of the antenna. We did not attach actual switches. We actually implemented ideal switches by directly connecting uh, with the copper connection. So these are more like ideal switches. Even then you can see the matching is good for all these, and the gain with actual switches gain would be less than this, sometimes by a dB or so, but because of the ideal conditions we are getting gain around 11.7 to 12.9 dBi. So these are the patterns, the measured radiation patterns, normalized beam direction as we predicted, changing between 31° for this pattern all once to 60° beam direction when all the switches are off, input reflection magnitude and measured gain. The key here is we need only two bias voltage values. We need some switches to be turned off, some to be turned on. That would be only two values, and sometimes that bias voltage could be, one of them could be 0, other one positive or negative value, depending on the type of switch, binary switch you use. These are the pattern cuts on the other plane versus. So this is the pattern cut over theta, and this is the other plane where the beam is wide. This is copolar pattern. This is cross-polar pattern. You can see the cross-polar level is about 10 to 15 dB relative to copolar. Yeah, so that's all about that antenna. Now this is another leak wave antenna. It's composite right and composite left type antenna. That is the type of antenna, the one I showed you, right? The first reconfigurable one, Carlos Ito one. It is of this type. They implemented this using gap capacitors and etc. Actual varactors. In our case, one thing you can understand is in a normal transmission line, if you take a small section, the standard equivalent circuit model has an inductor. There's no capacitor here, right? For an ideal transmission line. And for the shunt element, you have a capacitor, but no inductance. But to get composite left and right, you need a capacitor here in the series element, and you need the inductor here in the shunt element. So this can be achieved by adding extra elements to the leak wave antenna. You can add vias, shunt vias, to get this inductance, shunt inductance, and to get series capacitance. You can allow gaps in the transmission line. These are capacitors. So with these two, the transmission line becomes a composite right-left transmission line. The antenna becomes CRLH, leak wave antenna. Otherwise, we just feed as usual, so match load at the end, and it radiates. So what is the difference? This is S11 of this antenna. It's less than minus 10 over 2.56 gigahertz from 7.47 to 10.03. Now these are the radiation patterns of this antenna at various frequencies. So again, this is in this one there are no switches. It's not reconfigurable. So to change the beam direction, we change the frequency. We change the frequency just like normal standard Leaky wave antennas. And when you change the frequency from 7.5 gigahertz to 10 gigahertz, the beam direction changes from minus 40 degree here to plus 40 degree here. Now there is something special in this antenna that we did not have before. That is, you can sweep the beam, steer the beam across both sides, theta equals 0. Remember in one of the antennas we looked at before, Leaky wave antennas, when you try to go past, see like past the broad side or both side, the directivity drops, gain drops a lot. It doesn't really work. But this composite right left properly designed antennas can steer across both sides to the other side continuously. So like this, from negative theta with change of frequency to positive theta. So starting from minus starting from minus 40 degrees, going to plus 4 through both sides. That is important. See, going through both sides. So at 8.58 gigahertz, it's going right now. The beam direction is theta equals 0, both sides, and still you're getting a gain of 9.8 dBi. And that's for this purpose we need composite left and right. So some frequencies the transmission line behaves as a left hand, some frequencies behave as right hand. It changes the hand at this frequency, 8.58. There are a lot of papers written about this, Karu and some others, including our paper, so you can find some details. This is the total efficiency and radiation efficiency of the antenna. Total efficiency drops here at higher frequencies, but RF efficiency is pretty good anyway, both of them above 85%. Total efficiency is about 85%, radiation efficiency is about 92% over this frequency range. So those are the beam steering Leaky wave antennas of two types. One by change in frequency, one fixed frequency by changing the switches. So the other, there's one more Leaky wave antenna in my slides. This is something quite basic. If you want to get a beam in the both side direction, like the standard Leaky wave antennas don't radiate in both sides, as I said before. Only composite left-right ones or right-left ones radiate. But you can combine four Leaky wave antennas in a kind of a cross. These are all half-width Leaky wave antennas. You can see arrays of VRs here, and we combine them together. You can actually get a beam in the both side directions. So we published this in IEEE AWP Air, and we kind of, to make it easier, we did not match terminate these ends because there was not much power left. So we just put a VR at the end to reflect if there's anything, but it did not affect performance. This is the top view. You can see VR arrays here and here, and then the vertical segment has VR arrays here and here. That's our prototype. This is the input reflection. it works very good matching here from 3.8 to 4.1 gigahertz and some other high frequencies. So 3.8 to 4.1, that range. When you get to 4.1, the directivity drops, but 3.8 to 4.05, you got reasonable measured gain and measured directivity. But there's no beam steering. There's always the beam is in both side direction. So this is a fixed beam antenna. The measured match bandwidth is 300 megahertz. Measured both side gain is 10.1 dBi at 3.9 gigahertz and so on. So these are the pattern cuts, etc. So we will okay, I forgot about that. So if you want, you can actually, instead of 4, if you want a more uniform pattern, you can make 6 of those. We did not prototype this, but just simulated. And the other thing is, if you want to beam, so this one, the beam is in theta equals 0 direction, right? The idea was to get the beam in the both side direction. But this is different. Here we are getting a null in the both side direction by a very strong conical beam around it, narrow conical beam around it, using these hexagons. Sorry, not hexagon, it's a 6 linear arms of Leaky wave antennas. So microwave has attractive features, planar low profile configuration, ease of fabrication, inherent beam scanning. Fixed broadside or conical beam can be generated using an array of Leaky wave antennas. This is the last few slides. Significant improvement of bandwidth of a dual beam Leaky wave antenna can be achieved in one design. 2 side beams can be steered together. But I think this is quite unique, unconventional part of this lecture is the fixed frequency beam steering method. Without change in frequency, based on binary unit cells, you can implement it using any type of binary cell, pin diodes, any MEMS, etc. And it's desirable for mass communication applications because you don't have to change frequency and you only need 2 DC bias voltages, sometimes only 1, because one of them could be 0. So some of the things people can do: fixed frequency beam steering using low loss binary switches. Try different switches, engineer that design to something more practical. Methods to reduce gain variation with beam steering. There's some gain variation, you can optimize that. And also you can do in-band dispersion address in-band dispersion in fixed frequency beam steering. I did not mention in the beginning, but one of the disadvantages of Leaky wave antennas is they are inherently dispersive. So the beam goes in different directions at different frequencies. This can happen even within a relatively narrow beam width in a wideband system. Like if you have 100 megahertz bandwidth or 250 megahertz bandwidth in your channel, instantaneous bandwidth, the beam direction could be different within that band, and that is called in-band dispersion. So there are ways to manage that, but that is not an area possibly not very well explored. So you have seen this before. I think we are going to take a break now. But before the break, if you have a quick question, I think we got a couple of minutes. Anyone has a question? Okay, otherwise we will come back in, I forget, 15 minutes, right?
Sure, sir.
In 15 minutes, and then we will start the resonant cavity antennas. That is, we are a little bit behind the schedule. So finally, we get into resonant cavity antennas in the next lecture.
Sir, one question is there. Swapnil
Okay.
Shekhar.
Hello,
Yes.
sir. Am I audible
Yeah.
to you?
Yes.
Okay, sir. I wanted to know, like you showed one antenna which had varactor diodes in it. So I wanted to know, like when you were simulating it, do you also simulate the structure of the diode in the simulation? Because we can always put RLC element and then simulate, but the structure itself, how it affects the performance of antenna, or is it negligible that we don't need to do that?
Yes. In some simulations, we put a model of the whatever the diode or the switch.
Okay, so
And you can see difference in some cases due to the losses in the diode, especially in the gain. If you have multiple diodes, lots of them like our switched ones, and if you all of them are in a lossy state, uh, then that could produce in your simulation results a loss of gain and loss of efficiency, could be about a dB or so. So if you can try to do that.
okay, thank you, sir.
Okay, then. So we will return in 15 minutes. If you have any other questions, I can answer before we start the